Hi guys, I hope you're well. I'm just kind of tidying up a couple of concepts that aren't well suited to live lessons and are better done either in person or pre-recorded, and this is one of them. So today we're going to look at two things. We're going to look at IV graphs, so what happens to the current through a conductor as you increase the voltage across it, and we're also going to look at the kilowatt hour very briefly. So I'm going to very quickly just skim through these graphs first and then get to a more detailed explanation. So for a metal at constant temperature, you'll be quite familiar with this. As you increase the voltage, you get an increase in current. And if you notice, the rate of increase is the same. It's a steady line. So you increase the current, so you increase the voltage and you get a set increase in current. And because we keep the temperature constant, the resistance will stay constant too. So it's that nice straight line. In contrast, if we look at a filament bulb, which is essentially just a metallic conductor, but one that we don't control the temperature of. So this is allowed to heat up as more current goes through it. So this time, at the start, the graph looks the same. You increase the voltage and you get an increase in current. But this time, it's not a nice straight line. It's not a straight line. As you continue to increase the voltage, you're still going to get an increase in current, but you're getting less of an increase as you go. So as the voltage increases, you're getting less of an increase in current as you go. So the rate of increase of current has dropped. Now this is because the wire is getting hotter, the particles are vibrating more, and they're going to collide with the electrons trying to pass through them carrying charge. So therefore the resistance is increasing as the temperature increases in the bulb. Looking at a semiconductor, and we're going to be going into a lot more detail on this in a subsequent lesson, but the semiconductor, it's almost the complete opposite. This time, semiconductors actually work better at conducting electricity when they're warm. So at first, an increase in voltage doesn't give you much of an increase in current, but as ohmic resistance kicks in and things warm up, the semiconductor will carry more charge, so you get more of an increase in current as you go. It's kind of a strange one. We'll explain that in more detail in the next lesson. And the last three we're going to look at in a lot more detail. We're going to look at the IV graphs for electrodes in electrolysis for active and inactive. So with active, it looks exactly like the metallic conductor. An increase in voltage will give you an increase in current. And with an inactive electrode, it looks the same except it doesn't go through the origin. This time you have to apply quite a bit of voltage before you get an increase in current, and then it behaves exactly like a metallic conductor. And probably the most complicated one we're going to look at is the IV graph for a gas. So at first you increase the voltage, you get a linear increase in current, then it levels off, and then after a little while, after you keep increasing the voltage, you get another increase in current. We're going to explain why, so let's go into that right now. Let's start by imagining we've got a certain amount of a gas represented by these little blue squares, each of which is meant to be a particle of the gas. And now let's just focus on one of those particles. And you can think of one of those particles of gas as being made up of two parts, a positive part and a negative part, which most of the time are stuck together, but they can be separated. So for example, the negative part usually will just be an electron, and the positive part will just be the rest of that atom of gas. Or if it's a bigger molecule, the rest of the molecule. So you can think of a particle of gas as being made up of a positive and a negative part, which most of the time are stuck together, but they can sometimes get separated if they're hit by a bit of ionizing radiation, for example from background radiation or from cosmic rays. What this can do is it can hit the particle of gas and it can ionize it and separate it into a positive and a negative ion. So let's go and look at our collective of gas again. So there's a whole group of gas molecules bouncing around like crazy. Some of them are going to be hit by ionizing radiation and will be ionized, separated into a positive and negative ion. Most of them won't, but some of them will every now and again. And the ions will just bounce around a little bit inside the cloud of gas. Now, eventually, they're going to recombine, right? They're going to be attracted to each other, positive and negative. They're going to eventually encounter each other again and recombine to make the original neutral gas particle that they were before the ionizing radiation hit them. Okay, so we've established that a gas can be ionized, but so what? How is this useful to us? Well, we can use it to conduct electricity. So first off, let's imagine we've got a container, let's say a glass bulb, and we're going to fill it with some of that neutral gas again. And again, thanks to background radiation and cosmic rays, some of it will be ionized. Okay, so let's hook it up to a power source. Let's put a couple of electrodes in there, a positive and a negative. Let's close the switch and see what happens. I'm also going to notice that first off, you're going to create a potential difference between the two plates, between the positive and the negative electrodes. And also, let's chuck an ammeter in here so we can measure what happens to the current as we go. So let's look at the current voltage graph now. So at first, it's going to look very similar to a metallic conductor. As you increase the voltage, the current is going to increase because the particles now are going to be attracted to their oppositely charged counterparts. The positive ions are going to be attracted to the negative electrode, and the negative ions are going to be attracted to the positive electrode. But what you notice is that as you increase the voltage, you're going to get more and more of these charge carriers moving. But eventually, you reach a point where you've increased the voltage, but the current hasn't increased anymore. Now, what's happening here is all the ions that could be transferring charge are doing so. So you increase the voltage, but you're not getting any more current. Now, that's not to say that nothing's happening. As you increase the voltage, you're increasing the potential difference between the two plates. And this means that the ions are moving faster. They're going to be attracted with more force. Because remember, the potential difference, whatever you lose in potential energy is going to be gained by these ions in kinetic energy. So as you increase the voltage, the ions are going to be moving faster and faster and faster. And eventually, they're going to reach a point where they can be moving fast enough to hit the other neutral particles of gas and ionize them and knock off an electron. So now they're going to collide with the neutral particles of gas, ionize them, and boom, you've got more charge carriers to conduct electricity. So again, you're going to get an increase in current again. Our final set of IV graphs are much more straightforward. We're going to look at the IV graphs for electrolysis. So first we're going to look at one with active electrodes and then one with inactive. So active means the electrodes are part of the chemical reaction. Inactive means they remain inert. They just let charge pass through but remain unchanged. So let's have a look at our equipment. We've got a beaker or some sort of container which contains a solution. We've got a power source. The electrodes are the bits of metal connected to the power source which dip into the solution. And the charge carriers inside are called electrolytes. Let's throw in an ammeter as well so we can measure current as we increase the voltage and see what happens. So for active electrodes, that means that the electrodes are actively taking part in the chemical reaction, and you get kind of an immediate reaction on the IV graph. As soon as you turn on some voltage, you're going to get current being transferred. The positive and negative charge is going to be pulled towards their oppositely charged electrodes, and increasing the voltage will cause an increase in current. Again, linear, straightforward relationship, just like with a metallic conductor. Now, inactive electrodes are a little bit more complicated, so let's have a look at them next. Inactive electrodes just mean that they don't take part in the chemical reaction part. They'll allow charge to pass through, but they'll remain unchanged by the chemical reaction. Platinum would be an example of an inactive electrode that will be kind of unchanged in most reactions. Now, this time, if you ignore the power source for a moment, there's already a voltage difference between the two plates. There's already an electromotive force between the positive and negative electrodes. Now, to get any charge moving against that, you first have to overcome that EMF. So at first, when you increase the voltage, nothing happens. You don't get any current until you reach a point where the voltage you apply is able to overcome the EMF that already exists between those two plates. And then you get, again, just like with the metallic conductor, you get a constant increase in current as you increase the voltage. So the only difference between the inactive and active electrodes are in the inactive one, it doesn't pass through the origin, otherwise they behave in the same way. Finally today, and very briefly, we're going to look at the kilowatt hour. So because a joule of energy is such a small unit, it's not really practical to use for measuring how much energy a household uses. So in terms of like your electricity bill, a joule would just be too small. So instead we use the kilowatt hour, which is the amount of energy used by a 1000 watt appliance in 1 hour. So if you remember that a watt is a joule per second, so 1 kilowatt is 1000 joules per second. And if you're running it for an hour, it's just times 60 times 60, so it's 3.6 megajoules is 1 kilowatt hour, which is a more practical unit. And if you look at your electricity bills, it will give your usage in terms of kilowatt hours. All right, guys, I'll talk to you soon.